4 centuries ago, Galileo and his contemporaries were surprised to find our perfect sun was covered with spots that changed with time. This started mankind's discovery and exploration of our sun as a star.
We find that the sun is actually an extremely active star because of its magnetic field. Now that magnetic field waxes and wanes on this 11-year timescale, and we don't know why that occurs.
This magnetism was discovered just a century ago by George Ellery Hale. Since then, we have come to see magnetism as the key to understanding the sun.
The National Solar Observatory, with support from the National Science Foundation and the solar scientific community, is developing the Advanced Technology Solar Telescope. We are also developing some of the advanced technologies, such as adaptive optics, that make it possible to build this telescope. It will be the world's largest optical solar telescope, giving us unprecedented resolution and accuracy in studying the fine-scale magnetic field and solar activity that controls what happens in the solar atmosphere and beyond.
We know that the brightness of the sun affects climate. We know that the magnetic fields that extend from the inner part of the sun to the atmosphere of the sun out into space and finally to the Earth affect what happens here on the Earth.
That brightness varies just a little across the 11-year sunspot cycle. As odd as it sounds, the sun is brighter when it has more spots and dimmer when it has none.
In fact, we know that civilizations have come and gone probably in response to how the sun has changed. Climate changes were responsible for allowing the Vikings to settle on the west coast of Greenland, and climate changes were responsible probably for ending that culture. Climate change was probably responsible for a lot of what happened in the southwestern United States, the Muggiel and the Anasazi and the Hohokam.
The most striking changes in solar radiation are in ultraviolet and X-ray emissions. UV emissions form stratospheric ozone, a greenhouse gas that shields life on Earth from harmful ultraviolet radiation and may contribute to regulation of Earth's climate. Solar activity in the form of flares and enhanced UV emissions modulates ozone production here on Earth and thus directly affects the amount of radiation people are exposed to at the surface of Earth.
So we really need to understand the driver of space weather, as we call it, which is the sun, in a better way, and in particular the magnetic field of the sun, how that's generated, why it waxes and wanes, and the detailed impacts of these changes on the sun on the Earth's outer magnetosphere, upper atmosphere, and ultimately lower atmosphere.
On shorter timescales, space storms also affect communications and navigation satellites and power grids, and endanger airline crews and astronauts in space. The common cause is the magnetic field of the sun, which erupts as spots, flares, coronal mass ejections, and other dynamic events.
One has to understand that the sun, although it looks simple enough up there in the sky, is actually the most complicated object observed in the sky.
If you think of it in terms of energy, the sun's magnetic energy is only a very, very small fraction of its radiative energy. However, it absolutely determines everything that we see of the surface of the sun. All of these beautiful spots and loops, active regions, flares, ejections, all of the phenomena, the active phenomena that we see on the sun and also that we believe may happen on other stars, are there because the sun is magnetic.
The sun's magnetic field is generated by a large dynamo in which threads of the magnetic field are twisted, stretched, and amplified by gas flows in the interior of the sun. These threads eventually emerge at the surface in the form of sunspots and smaller magnetic structures. Current telescopes are like magnifying glasses that let us see the threads of these structures. To understand how the field is brought together and evolved by the gas flows, we need the ATST microscope that will reveal the warp and woof of the fibers within those threads.
Most of the changes that happen on the sun are caused by changes in magnetic fields, and the ATST is a very specialized instrument that allows us to see those changes, and it in fact has a sensitivity to measure changes in the magnetic field at the same kind of magnetic field strength as the changes that exist, or the magnetic field that exists on the Earth and makes your compass needle work.
While spacecraft have opened the heavens to us in many new ways, ground-based telescopes avoid many of their costs and disadvantages.
We need ground-based solar telescopes because many of the problems that you face with the sun involve very high resolution, very sharp pictures of the sun, which to do from space would be extremely expensive.
The sort of science we need to do to look at the details of the magnetic field on the sun require extremely high resolution, which requires a very large telescope. The cost of putting a very large telescope in space is completely prohibitive.
Until recently, such a large telescope was not practical because of blurring by Earth's atmosphere. New adaptive optics technologies let existing ground-based telescopes observe details many times sharper than what was once possible. But to see the smallest fibers of the magnetic field, we need images 33 times sharper than common telescopes can produce, which requires a primary mirror 13 feet in diameter.
At last, it seems as though the technology with adaptive optics to take care of atmospheric seeing has gotten to the point where we can address the really basic problems. The extremely small, violently active magnetic fields that control the temperature of the corona and the solar wind, that produce flares, that produce X-ray emission, and it's now technically within our grasp, and it's best done with a ground-based instrument, typically 4 meters in diameter.
Adaptive optics technologies let ground-based telescopes see as sharp as orbital telescopes. Already, existing telescopes hint at new discoveries that lie beyond the limit of current resolution. They also show that we need to do more than take pictures. We need to make movies.
What we've learned maybe over the last 10 or 20 years is that things happen incredibly quickly on the surface of the sun and on a very small scale in terms of kilometres or miles, and we need to be able to track these very quickly in time. We need to be able to see how they change really on timescales maybe of seconds or minutes.
Being able to see those changes at fine scales as they develop will be like the difference between barely seeing a hurricane and being able to track its birth, growth, and impact. Ground-based telescopes also play an important role in educating new generations of solar scientists.
As you develop new instruments to put on the telescope, your students can become trained in development of instruments, in the use of instruments, and it's simply a much less expensive place and far more effective for education as well as pursuing many aspects of the science.
And like students, ground-based observatories can grow and improve over the decades.
We can change the instrumentation behind the telescope on the ground much easier, of course, than we can on anything in orbit. So a ground-based instrument allows us to do new science as new science evolves, as new instrument techniques come along, as new technologies evolve.
ATST's unique design provides even more capabilities. With a clear light path between sun and instruments, ATST will observe from near ultraviolet through visible light and deep into the exciting unexplored infrared spectrum. This open optical path will also let us explore magnetism in the sun's ultra-faint corona as well as on the disk. Already, a new infrared camera on a smaller telescope has discovered long-sought magnetic waves in the corona. An exceptional design also requires an exceptional place, an island mountain with little turbulence to blur the view or moisture to block the infrared spectrum. From a list of 72 possible locations, NSO selected sites in the Canary Islands, Mexico, New Mexico, Utah, California, and Hawaii for testing. Survey towers gathered 2 years of data on seeing conditions, such as how bright the sky gets near the edge of the sun. Of all the sites, Haleakalā, as it rises above the lower turbulent layers of the atmosphere, had the darkest, clearest skies.
We have to have a sky which doesn't cause distortion of the image, so we can see with crisp detail the fine and the small features in the atmosphere of the sun that connect to the big events that produce, for example, the explosions that we feel here on the Earth. If you get up high enough in a tropical site over the ocean, you get above what's called an inversion layer, and up there the air isn't very turbulent, and the dust and the debris from lower elevations doesn't make it into the sky above you. And for most locations on the Earth, this blue sky is in fact an indicator of a bright sky that interferes with our ability to see the sun's atmosphere that stretches into space and extends, in some cases, all the way to the Earth. And so that's really the reason why Haleakalā becomes a unique and an important site for doing these solar observations, because it's in the tropics and it's high enough that the site pokes up above the turbulent layer.
Today, the ATST project is ready to move forward as a partnership of the NSO, the National Science Foundation, the University of Hawai'i, and many others. We also seek partnerships with educational and other institutions in Hawaii to help train the next generations of scientists, observers, and operators who will use ATST.
The ATST is new technology. It represents for us and for mankind a jump in capabilities from the ground, which is larger than any jump since the age of Galileo.
You're better off working it from the ground now that we have adaptive optics, where a telescope placed on a truly excellent mountain site can begin to see sharply enough to see the activity on the sun.
It's not just a telescope, and it's an instrument that measures and monitors and hopefully will teach us to understand and explain and even predict the changes in the sun that affect what happens here on the Earth.
It will revolutionize our understanding of solar magnetism and the activities that impact the Earth, our environment, and our civilization.
The combination of exceptional seeing, exceptional capabilities, and exceptional people will provide an observatory serving the nation and the world through the 21st century. With ATST, Hawaii will lead the world in studying and understanding the star that is closest and most important to humankind.